Uh, so syllabus is here, and we are going to finish just a little bit of the quality lecture, and then we'll get into part one, to be followed by part two next week on spin echo sequences, followed by gradient sequences. And next week, I have a quiz, but I think I'm just going to give it as an assignment. It's just 10 questions. So I'll send it to you, and then you guys hold on to it and email it back to me. Or you know what, just whenever you're ready to email it back to me, email it back to me. You have a week to do it. And it's on waiting. But of course, you can look things up, and hopefully everyone gets 100, right? Okay, so that's the syllabus. Okay, so we have no changes really. The 15th, we're still going to take that day off. So that's the 15th, right? So we're going to do 4/8, and then April 22nd. April 22nd, we have 2 lectures, but they're both pretty quick. Then I have a review. So I think this day had spring break in it, maybe. And our last day will be the final exam, but of course I will send you emails with what you got right and what you didn't get right. And so you'll hear from me after this, but that's the day we'll take it. And here's an extra presentation that you're going to want to study on your own. It's related to artifacts. And I usually don't deliver this because it's one of those things where you have to identify the artifact and figure out how to fix it. So the presentation of that is just very cut and dry. I would literally be reading it. So you might as well just read it. So that's yours. So today, let me go back to the quality lecture, which I have up here. And can you see the presentation?
Yep.
Okay, good. All right. Sometimes I have to like close it and then reshare. So I'm just going to, oh, well, one last thing. Can you see this table?
Yep.
Okay. So we had a question during the presentation, like what was better, a square voxel, right? So that's the volume element, kind of like a sugar cube, or a rectangular sugar cube. And there are sort of pros and cons. So I narrowed it down because I did have a table with sort of all this other stuff in here. So I narrowed it down to the more important ones, which are these kind of 5 aspects: scan time, resolution, partial volume, signal to noise. If you ask me, that's maybe at the top with scan time, and sort of clinical applications. And then I asked for the table to give us another column with an example here. So generally speaking, it's going to take longer. So scan time might be 8 minutes versus 5 minutes if you go with square voxels. So you can reduce the scan time pretty dramatically. I don't know what percentage that is, right? But that will help. Resolution, square resolution is going to have all dimensions the same. So kind of like a 1 by 1 by 1 versus a rectangle, something changes. So you see it's got 0.5, 0.5, and 2. So you get a higher resolution with the rectangle but only in certain dimensions, right? So it depends, what you're scanning, right? And the example here is in uh, spinal cord imaging. I'm going to skip partial volume. You can look at that, and you could look at clinical applications, but the next kind of biggest one is here you kind of have a balanced signal to noise ratio that's kind of nicely oriented in all three dimensions. Whereas, again, similar to resolution, when you go with the rectangle, you're going to only optimize the signal to noise in kind of like two directions versus three. So if that's okay with whatever you're doing, then you can use a rectangle and essentially save time, right? Usually with the reason why in this example, it's 1 by 1 by 1 for a square matrix is usually we're using square voxels when we are going to be using thin slices, right? And that's going to definitely increase the scan time. It's going to increase the computer usage. So it really depends, right? There's no only use square or only use rectangle. It really is based on, do you need resolution in all three dimensions or only two dimensions okay? If you do go with the rectangle, you can save scan time. That also can help reduce motion because we don't want people to move around. So if you can make the scan faster, that's a good thing. Okay. So let me make this bigger. So we have some common parameters, right? A short TR is around 400. Remember, TR is from your 90 excitation pulse. Well, it doesn't have to be 90. It's from your excitation pulse to your next excitation pulse. If you want kind of full relaxation to occur, and you want a very high TR so that you can do, let's say, T2 weighting and knock out all the T1, somewhere around 2,000 to 2,500 milliseconds. That's a very long TR, for example. Long TE is about 100. So, a long TE is always pretty much shorter than, TRs anyway. And that kind of makes sense because if you remember the pulse sequence diagram, and we're going to see some more of them today, you'll notice that the TE is kind of always embedded within the TR. So you have the excitation to the next excitation, but right after the initial excitation pulse, not long after that, I should say, you get your TE, which is your time to echo. Flip angle, which when you maximize your flip angle, the higher it is, the more signal you get. But a relatively low flip angle is about 20 degrees. We'll see this next week when we talk about gradient sequences and we talk about things like the steady state. And, a pretty thin slice would be about 4 millimeters, right? But you can go even smaller, right? Because if you go back to the little table that I saw, and we saw that example of 1 by 1 by 1, we can get this down, 75% more to like a 1 millimeter slice. And a small field of view is around 12. And this is just saying that, you can cut down dramatically without changing your spatial resolution just by going down about 1 millimeter, right? And that'll change your signal as well. When you reduce the voxel size, though, signal goes down, right? When you have a smaller bucket, signal goes down. This was taken from your book. It's a super good study sheet. So if you were to put these things on cards or memorize them, the idea is, at least for most of these, I try to explain how it works and why it is. But at the end of the day, if you know that TR up, signal to noise goes up, but scan time goes up, that's the limitation. If you have these kind of down pat, this will go a long way to passing the registry. So super important slide here. Okay, so there is something called volume imaging. And this is when you have like a slab of data, a volume. Sometimes we use this with vessels, with angio. There's no gaps in between, right? And you have very thin slices essentially. But what happens is the slicing coating gradient has to go off yet again, which is why you get, this is kind of like multiple K spaces kind of put together. So it's going to take time and energy to do these things because you have to have very steep gradients for all of these. But it will allow you to see kind of small little lesions, which can be very, very helpful. Like I was saying, the disadvantage, though, is scan time is going to go up. And speaking of scan time, here is our formula for scan time. So scan time is going to be the TR. And we know that this is directly proportional. So if this doubles, the scan time doubles. Times the next, remember that was that do-over where you fill K-space, but if you have a next of 3, you fill it again and then again, right? So next of 4 means you're filling it 4 times. So obviously that takes a lot of time. The number of phase encodings, which is when you're looking at K-space, how many horizontal lines do you have? Do you have 64? Do you have 128, etc., right? And then how many times you encode the slice. So you multiply all these together. I think we talked a little bit about this, and you get a big, big number in milliseconds. You then have to divide by 1,000 to get seconds, and then divide by 60 to get minutes. That way, when you tell a patient they have 6 minutes left, it's understandable versus they have 3,800 and something seconds and make them do the math. That's not nice. So when you have an isotropic voxel, remember that means all 3 dimensions are the same size and they're usually small, like 1 by 1 by 1, or maybe even less. So volume imaging, particularly good for joints, small little lesions, right? Again, it's going to take longer, right? And was that it? I guess that was it. Okay. Moving on. Unless you guys have a question on anything we did in here. This was a fun one. I think you got your money's worth last week on this one. All right. Let's stop that and pull up the other one. Give me 1 second. Okay. And let me share it. I see a couple of you are probably looking at it already, which is fine. Okay, here we go. So here is a kind of macro pulse sequence diagram. We have our excitation pulse. We know that this is a spin echo, not just because it says spin echo, but every spin echo always starts with a 90. Usually gradient sequences are less than 90, not all of them. But if it's anything other than 90, it is not a spin echo sequence, right? It falls into the gradient sequences, followed by, the way you read these is we go down and to the right. So the very next thing that happens actually happens simultaneously. So 90 excitation pulse, and you have your free induction decay. Then going a little bit further in time, you have your 180-degree rephasing pulse. And that is going to get our protons that are starting to point in different directions. So remember, the term phase is direction. So the problem with T2 star, because of all the magnetic inhomogeneities and how hard it is to actually create a very nice homogeneous magnetic field, causes these protons to start to spin or precess at different frequencies. What fixes it momentarily is this 180-degree kind of reversing effect. And what that will do is it kind of snaps everything back together. We'll go over it again. That said, the next thing that happens is after you have rephased, you then get your echo. And your echo happens at TE. So TE goes from the excitation pulse to the center of the echo, not just any part of the echo, but the center signal of the echo. And they split it up into half TE, but that's not that important. So one half is from excitation to rephasing, and then from rephasing to readout of the echo. So there are lots and lots of sequences, right? And there's more and more, and there's proprietary ones, and then there's, spin echo is kind of like a gold standard. Everyone has their version of flares and stirs and spoiled sequences, echoplanar imaging. So this is actually from a document that I'm going to send to you, where when you click on this, it takes you to a different part of the PDF. It used to be an interactive PDF, which was really cool. It had animations built in through Flash. Of course, that doesn't exist anymore. So that document is still good, although the pictures don't move and do fun things. You can still see the buttons that you're supposed to press, but unless you're able to go in the Wayback Machine or figure out how to get Flash running on anything, you won't be able to get those. So each one is about 3 or 4 pages of this much larger PDF. And each page gives you a little bit of the physics, a little bit of information. It's really good. So I'm going to send that to you, and we'll probably pull it up at some point also. Oh, so, it's not that one is red and one is green. It's just that this is one type of sequence that, as you can see, there's other sequences within them. And then you have the gradient sequences. And these are the family, so to speak, that keeps growing, right? That's where the technology is going, because overall, right, a spin echo sequence will give you very, very nice signal. So that sounds good. Why are we moving away from it? It's because the gradient sequences are much, much faster, and the signal is, this is a technical term, okay-ish, right? It's not as good, but you save so much time, right? So that's where we're progressing. So here's a spin echo sequence. We know it is because we have the 90 and the 180. This is a gradient sequence because it's something other than 90. So it's known as a variable flip angle, meaning it's not always the same. We also see the 3 gradients here. We have the slice select, phase encoding, and frequency encoding. Then we have a readout of the FID and the echo. Notice the spin echo has a nice big signal, and the gradient sequence pretty small. So we're going to go into what these things mean, of course, so don't worry about that. But what I do want to mention is you've already seen like 2 different looking things, right? So pulse sequence diagrams are just that. They're diagrams that represent timings of different events that the computer knows, but we're trying to graphically represent that. So it's kind of like asking like 3 or 4 people to draw a map, right? They're going to have the same kind of things, but they're not always drawn exactly the same. Right. So we're gonna see that. So when it comes to the sequence stuff, this is where I diverge a little bit from the textbook, because of course the textbook has one artist and draws everything the same way. And the registry is going to have some artists who might draw things a different way. And any number of other articles and websites and materials that you look at are going to have pulse sequence diagrams, but they might look different. The idea is you want to learn enough so that you can recognize, even though something might look a little different, what it is, right? But usually there's a line for the RF. There's 3 lines for what's going on with the gradients, and then there's a line that's showing you the signal, and these things repeat. So we'll talk about kind of what's happening when things go up, when things go down. Why does this look like a bunch of different dots? So we'll get into some of these things. So that's just it again, right? The pulse sequence diagram is going to show you when the gradient is applied. It's going to show you when RF is applied. It's going to show you the signal. And you should get to a point where you can look at a sequence diagram and understand what's happening, like be able to call it an incoherent gradient sequence. So again, it's something you kind of have to memorize, but this is also where clinic will help as well. So the major components that all sequences have, whether they are, spin echo or gradient sequences, is that they all use RF. They all have some kind of excitation pulse at the very beginning, whether it's 90 or something variable, and they all use the gradients to spatially encode. And some sequences use the gradients to rephase, which is what happens in gradient sequences. And other sequences, basically the spin echo sequences, use another burst of RF to encode the signal. I'm sorry, to rephase. So either you're going to rephase with a 180, or you're not going to have a 180 and you're going to rephase with a gradient. So if we go back up, right, here's our 180. Notice there's no 180 over here, right? So one of these gradients is going to do double duty, right? And by the way, they're super duper fast, right? We've been talking about, relaxation time and T1 and T2 times, all in terms of milliseconds, but the gradients are microseconds, if not faster. So a microsecond is 1/10,000th of a second versus a millisecond, which is, 10 times off from that, right? So I think the gradients might even be going at like picoseconds, which is like is it, no, not 10th, is it a millionth? I don't know if they're that fast. I'm pretty sure microseconds, right? Which is what we used in figuring out the slew rate once upon a time. It's the U with the stem on it symbol, kind of like draw a U and then bring down the symbol a little bit more. So all sequences are going to spatial encode, and that consists of slice selection, phase encoding, and frequency encoding, in that order. Okay, so what are we going to talk about today? We'll talk about conventional spin echo, a slightly faster version known as fast spin echo or turbo, and then we'll talk about inversion recovery and what that's all about. We will, next time around, get into more stuff, which is the gradient sequences. There's a coherent versus an incoherent. They're basically opposite of each other. There's steady state free precession, which is basically a cousin of the coherent echo. and then there's some faster sequences. We will also talk about some specialized sequences when we get to flow and flow phenomenon, which is the angio stuff, which takes on a whole different ball game. We have a whole presentation just for flow. So here is a conventional spin echo sequence, right? We're seeing that very first slide that we saw before, but we're not seeing the individual gradients. Again, they offer very high signal to noise. They can be used for T1 or T2. You'll see that other sequences don't do everything. The spin echoes are very versatile and they have good signal. Again, we're moving away from them though, because they are very slow. Even the fast spin echo is slow compared to the gradient sequences. Better than the, original vanilla spin echo sequence, but still, and you're going to see it is much faster, but yeah, when we get to the steady state, it just takes on, I don't know, it's like fast spin echo is like a race car compared to a horse, but gradients are like that sports car compared to like a rocket ship in space going, going 20,000 miles an hour. So spin echo again, the T1 weighted images have very nice signal. They're good for anatomy. T2 really pulling out on that fluid content. I think the MRImaster.com site that I may have showed you on the first day has a lot of good images comparing T1 to T2 and what the different grade, as well as proton density weighting. But T2s definitely pull out the stops when it comes to demonstrating fluid. And what do we have when we have masses and tumors and a lot of pathology is kind of a sort of what I call a squishiness factor, right? There's a lot of extra fluid content that can be pulled upon and imaged. So spin echo sequences, before you start looking at the numbers, don't get too caught up on the terms short and long. I know we've been using them, but you will see that when we go from spin echo to gradient, especially when we go to the steady state, those long and short term words are still in there, but they're completely different from the range that you have in spin echo, right? So, if you want to remember the short TE for a T1 might be 10 to 20, but when we get to some really fast scans, we're going to get that down to like 1 millisecond or even less. So they're short and then they're short, right? So what you do want to remember is usually when we're doing T1, right, we're trying to keep our TR short, right? And we're trying to keep our TE short because we don't want T2 and we don't want complete relaxation. Excuse me. Let's skip to this one, right? A long TE, we want a certain amount of decay to occur. And here's what I was talking about. Nice long TR, 2000 milliseconds. That knocks out all the T1 information, leaves you with T2. But does take a long amount of time, right? We have 4 to 6 minutes. That's basically because the TR is much less. If you think about it, right, 700 goes into 2000 3 times, right? So 6 times 3 is 18, and this is 15. It's in the ballpark, right? Kind of proportional to each other, basically. Proton density, we're doing the opposite. for T1, which is a long TR, and the opposite for T2, which is a short TE, to basically knock both of them out so that our contrast is coming simply from the quantity of protons. Remember, with proton density weighting, the more protons that a tissue or pathology has, the brighter it shows up, right? Higher signal. Okay, so fast spin echo. But to backtrack for a quick second, so spin echo is simply 90, 180, 90. And after the 180, you get an echo. 90, 180, 90, another echo. 90, 180, 90, another echo. And each one of those, so I did it 3 times, would be one horizontal phase encoding line within K-space. So 90, 180, 90, fill a line of K-space. 90, 180, 90, fill a line of K-space. You have 64 lines, you got to have 64 TRs. Fast spin echo allows you to fill multiple lines of K-space per TR. So you might be able to fill 4 lines instead of just 1. And then essentially that scan would be 4 times faster, right? Because instead of having, let's say, 64 TRs to fill 64 lines of K-space, right? You would have 64 divided by 4. You would only have 16 TRs instead. Okay, so we're going to fill multiple lines of K-space. Now, our TRs do need to be a little bit longer because if we're going to try to do a very fast spin echo and fill like 16 lines instead of 4 per TR so that it'll be that much faster, you can't have a short TR. It just won't work. So how does it work? Instead of having 90, 180, 90, and remember you get an echo for every 180-degree rephasing, we're going to do 90 followed by successive 180s. So something like 90, 180, 180, 180, 180, 180, and then eventually a 90. And we call that the echo train length, or the echo train, or ETL, echo train length. And it's going to look like this. So how many echoes? You could count down here, but you could count up here. 1, 2, 3, 4. So that means it's going to be 1, 2, 3, 4. So we start with our 90, then we have 4 180s. It doesn't have to be 4. It could be 5, it could be 16, it could be, I don't know what the highest amount is. 16 is pretty high. Here's our slice select gradient again, phase encoding, frequency encoding. Here's the echo. This is our FID. Now, while we're on this screen, let's kind of go over a couple of things. So this is the slice select. They look like they're all the same. Their amplitudes are all the same, which means the slope of the slice select gradient is the same. When will it change? When you enter and fill all of K-space and you're ready to do the next slice. It'll get either a little taller or a little bit shorter. Now compare that. I'm not going to talk about the stuff going on underneath right now. Compare that to this one, which gets shorter and shorter and shorter. That's the phase encoding gradient. That is literally the slope changing on the phase encoding gradient, putting you into a different line of K-space. So it's still the same K-space. That's why these aren't changing. It's representing one slice, but different lines within that K-space. Now, let's not focus on this one here. let's talk about the real echoes. So the readout, the frequency encoding gradient, they are always centered directly on top of a gradient. They might look like a box, or they might have a little angle to it. You know, people draw them slightly differently. And this is the width of this represents our bandwidth, our receiver bandwidth, whereas this is our transmit bandwidth. And I'm going to show you, I think, on another picture what this XMY means and how this could have been drawn a little bit better. Because there's something going on here, right? And we'll talk about the EFF in a minute. So the basic premise of fast spin echo is the number of 180s give you the number of echoes. I just lost everyone's picture. Where'd you guys go? Hold on. Oh, here you're back. Okay. So the number of 180s gives us the number of echoes, which means how many lines of K-space are filled per TR. Sometimes the number of echoes is known as your turbo factor. I like ETL, echo train length. Here's another fast spin echo sequence. Notice it's drawn a little bit differently. This looks like it's supposed to be twice the size of this, so I think the drawing could have been better. Here's our slice select. It's spelled out instead of GS. They actually spell out the word slice. That's nice. Here's our phase encoding. And instead of looking like these or these, it just looks, where are we? It just looks like a block with an arrow up or an arrow down. But same thing is happening though. We're still in the slice. This is 1, 2, 3, 4. Also has a ETL of 4. Phase encoding means our phase lines. The readouts, those are the same. Usually the bandwidth does not change in the middle of a sequence, right? So this particular gradient is going to have an easy day. The phase encoding is going to go crazy, and the slice is going to change depending on the slice, but the readout is going to be the only one that's consistent. Remember, this is also known as the frequency encoding gradient, and they're still centered. Now, I mostly don't like this illustration, except for one thing. Here is our echo for our first 180. Look at the signal for the second one, and then the third one. And then if you look really, really close, you could see that teeny weeny baby one over here. That is the trade-off, okay? That's the MX curve. Here, you're showing it where the signal is definitely going down. So the more 180s that you have, the faster you can fill K-space, but the worse your overall signal will be. Let me say that one again, because that's like important stuff. So your ETL, when it is increased, when you have more 180s and you get more echoes and you can fill K-space faster because you won't need as many TRs, the trade-off is that your echoes will get decreasing signal for every extra one that you try to fit within 1 TR, right? So if you try to have an ETL of 4, your last echo is not going to have the signal as your first. And if you then do another sequence where you kind of double that, so now let's say your ETL is 8, that's going to have overall worse signal. It's going to be twice as fast, but it's not going to look as good. Okay. Oh, I just made it bigger so that you could see it. That's all I did there. Oh, let me go backwards. This MXY curve here is trying to show these echoes getting smaller. I don't think it looks as cool or as good as this, right? This dramatically shows them getting, getting much, much smaller. Right? But I have to say, I don't like the rest of it. I don't like how they drew any of the other stuff. So, now, don't look at the bottom yet. Just look at the images. Which one looks better, left or right? Grant, what do you think?
Left.
Yeah, I think, well, you weren't Grant, but okay. Left, I agree. Left, this spot is brighter than this one. You have more signal here. But is the one on the right absolutely terrible? It's not. And I'm going to give you another reason why we can do this also. So first of all, this brighter image took 7 minutes and 17 seconds. With an ETL of 16, the fast spin echo sequence on the right only took 34 seconds. That's 7 minutes compared to 34 seconds. And it's not terrible. And the other thing is, you're not just doing one sequence, you're doing multiple sequences. You have lots of different data and information to look at. So if you kind of speed up one part of the sequence, but keep other parts the same, it's just one study that is going to be a little bit less time. So you save time and make more money, right? Kind of like shove more patients into the scanner, right? You used to have like 45 minutes between, now they're getting people in there in like 15 minutes. It's never going to be as fast as CAT scan, but it's getting faster.
Does
Well,
it
but the
matter
point
what you're
is,
looking for also? Does it matter what you're looking for sometimes?
sure, yeah. So, this is definitely a better image, but this isn't the only images it's not like this is the only image you get for the entire study, right? I mean, you're getting lots of other information besides this. Okay, now, here's an interesting question. So we know the TE has an effect on weighting, but when we do a fast spin echo sequence, there's actually multiple TEs, right? Because if we look at the definition, from the 90 to the center of the echo, that's one TE. From the 90 to the next echo, that's another TE, etc. From the 90 to the third echo is another TE. So if we are going, whoops, I don't want to give the answer away. If we are going to have multiple TEs, how do you weight the image? Like, how do you have a longer or a shorter TE if you have more than one TE? And it's not as complicated as you think. It's actually pretty simple. Okay, so much for class participation tonight, guys. All right. We're just happy that Butch and Sonny are home and they can, finally walk their dog or whatever. I don't know where I saw it. People were like, oh, I think it was Gail on CBS. She was like, how long do you think it's going to take for them to get back to, like their spouse tell them to like do the dishes and mow the lawn? Like, a week or two? before they have to do all that stuff again? Okay,
Yep.
the answer is you just pick one, basically. You pick a TE to use, even though there's multiple ones, you pick one of them to be the TE time for waiting. And that's what we call, and I mentioned it before, and I told you I'd talk about it later. That's what we call the effective TE. So that is what this means, EFF. So how do you do it? If you want a shorter TE, you go with one of the echoes towards the left or one of the TEs towards the left, right? If you want a longer TE, you go with one of the ones towards the right. So it depends on whether you're trying to do T1 or T2. You just pick one TE that will be effectively used for the weighting of the image. This is kind of a refresher, really. We've already talked about how when an echo is placed towards the center of K-space, it's going to be the one with the highest amplitude signal. And we get to that part of K-space by utilizing the phase encoding gradient. And when we activate it, we don't spend a lot of time because we're going to have a very shallow slope. Whereas information that's placed towards the top or towards the bottom of K-space, so we call that kind of the periphery of K-space, those are the low amplitude signals, but they represent the spatial resolution. They represent the sharpness of the image. So it's the combination of all these lines. Again, not that you actually have to collect every single one, but the more data that you have, the better your image will be. But you can save some time by cutting out a few lines of K-space. So it's the amplitude, right? The steepness of the slope that determines where in K-space you go. So that's the slope being applied to the phase encoding gradient. And remember, when we say that, we're not at this point being given enough information to know whether it's actually the X, the Y, or the Z gradient. All three of them can do phase encoding. All three of them can do frequency encoding. Okay, here's an easy one for class participation. What spatial encoding must be done by certain gradients? It's the only one I didn't mention.
Y bigonal?
So that is correct. It's not the full answer. It's kind of like an example. So what I mean by that is when it comes to slice encoding, a specific gradient must do a specific slice. And you mentioned Y does coronal, which is true. But you could have alternatively said X does sagittal or Z does axial, right? So all three of them can do phase encoding and frequency encoding, but only a specific gradient can slice or do slice selection. Okay, so what you can see here is we can take our echoes and we can reposition them. This is where it gets a little weird. And we can put them into K-space. So in where we want, essentially. And this looks like it's kind of traditional because this large signal is getting put, right in the middle. Yet the small one is going, towards the top. There's also something interesting going on. I want to make this image bigger. See if that works. Yet another way that someone drew the phasing coding is they just took these rectangles and they put a different horizontal line indicating it's a different slope, and each one is being placed into a different part of K-space. So everyone draws things in all sorts of different ways. You just have to kind of, I don't know, teach it for 10 years and then you'll get it. No, I don't know. You just have to watch out. Everyone has their way of doing things. It's like when you have, 10 people draw a house with a crayon. Everyone will be able to recognize like the door and there's a chimney and a window, but things will be, positioned a little differently. And we just have to learn how to recognize all of that. Oh, there, I looked at the right time. They're getting out of the capsule now. Takes time. Have you ever seen a splashdown with the SpaceX module capsule? Yeah. They have to tow it to the back of this boat, and then they put it on this thing. They kind of like wench it up and like bring it down, and they call it like the bird's nest or something. They're putting the little thing in like the bird's nest. It's still going to take them a while because they got to check for like leaks and they don't want anything to like blow up. Don't worry, you guys will catch like the 30-second thing on the news. I'm a glutton for punishment. I watch like 3 hours of the thing like docking to the. It's like, we're there. We only have like 2 inches to go, and that takes like half an hour. But hey, you can't mess with stuff. It's dangerous in space. Okay. Speaking of space, I am not going to space, but I am doing a lecture on space medicine, which should be fun. I've been working on it. I will share it with you when it's done. Oh yeah, so they have to slide them down because, oh, that's sunny. All right. Yeah, so I'll describe this to you. There's 2 guys that are basically lifting her off of a little slide, kind of like the thing that you put underneath a stretcher to like transport the patient over from like a bed to something. And now they put her on this sort of wheelchair, and she's waving and happy. So it's like their arms work, but they still had to take her away on like a wheelchair. They do that for all of them, though. Yeah, so I don't know if you guys have stock in Boeing, but Boeing went up. It was an experiment. I mean, they got to the point where they put them in it, and then it had mechanical difficulties, and that's why they got stuck up there, because they didn't want to send them back down, even though it turns out that they could have, because they sent the capsule back and it did okay, but they didn't want to take that chance. So they had to wait so many different cycles, and different astronauts from other countries all trying to, figure out when they can get them home. It's not as easy as like, missing a train or a boat on Earth, right? There's only so many ships going up. And unfortunately, it took 9 months to get them back. But they're back. And they seem happy. Okay. So fast spin echo has pretty much replaced old conventional spin echo, right? Because the images are not that much worse, as we saw before, even with, and that was an extreme example, right? I mean, to go back to that for a quick second, this was at a ETL of 16. You have to imagine if it was an ETL of half that, like 8, or even less, like 4, then the difference between the two, you wouldn't save as much time, but it would be a little bit better, right? So it doesn't have to be this, I don't even want to say this bad, right? Because I don't think it's that bad. Okay, so problem that you have with spin echo or fast spin echo is that fat remains bright on the T2. Repeated RF pulses, right? So having that extra RF, which is 180, 180, 180, 180, etc., that can increase something known as magnetization transfer effect, which is basically a blurring. So it might be harder to see very small hemorrhages. So, Nestor, there again, it does depend, like you said, what they're looking for, right? If they're specifically looking for small hemorrhages, maybe you don't go with a very high ETL, or maybe you don't use a fast spin echo sequence at all and just go with the gold standard, right? So there are some downsides, but for the most part, it's the fast spin echo or turbo echo has replaced conventional spin echo. So fast spin echo, TR for T1. So remember, T1 weighting, TRs are not going to be that high. So notice 300 to 700 versus 3,000 to 10,000. Okay. Effective TE, we're going to keep that as low as possible so that we don't get T2, right? So that's the meaning of minimum. Now, turbo factor is 2 to 8, right? That means 2 to 8 180s, right? So you'll be able to fill K-space 8 times faster if you have the max. Okay, proton density, we're going to keep the TR really high. We're going to keep the TE really low. So again, that's anti-weighing or minimizing any T1 and T2 effects so that we're left over with proton density. Right. Now, for T2, this one's pretty interesting. For T2, we still have a long TR because we don't want T1 information, but we're increasing our TE, right? So now we have around the 80 to 140, but because we have this nice long TR, we can really up the turbo factor and speed up the scan. So a T2 weighted fast spin echo can be, let's see, what's my times table? 8, 16, 24, 32, can be about 4 times faster, right, than a T1 weighted fast spin echo sequence. Because here we're going from 300 to 700. Here we have 3,000 to 10,000. What I really should have pointed out, the way I did my math, was if we have a turbo factor of 8, which is a quarter of 32, but close enough, that means that this one here is going to be 4 times faster. Right. I would ask that question on a test, I think. I think that's a good question. Makes you think, right? It makes you compare your, so there's that word again, effective TE. Okay. So, anyone want to tell me if this image looks good? Does it look kind of mallow to me? Looks bad. It's blurry. This was an attempt to fill all of K-space in 1 TR. That's it. 1 TR to fill everything. And that's why it's called single shot, or SSFSE, single shot fast spin echo. It's like, but it's kind of fake. What it collects is actually 1/2 of K-space in one TR. Now, you can't have a huge K-space. You can't have, 256. So this is only going to work for like a small K-space, like 64, where you have 32 lines going up and 32 lines going down. And what it will do is you'll have 32 ETL. So 90, 180, 180, 180. No, I'm not actually going to do it 32 times, right? And then once you have that, so bullet, I guess is the second bullet. Looks like there's one missing. This one here where it says utilizes the partial Fourier technique. This is based on when we talked about K-space, we mentioned that there's a symmetry to K-space. Do you remember that? Kind of like butterfly wings. There's like the left side matches the right side and the top half matches the bottom half. So in this case, we fill the 32 top half lines, and then we would transpose using this conjugate symmetry, they call it, the other 32. That way we fill all of K-space, so total 64 lines. But this is bad, right? It's super fast, but now similar to the issue with fast spin echo that we said each echo that you use gets diminished and your overall signal goes down. This is really bad, right? We've hit the limit. We tried to fill all of K-space in one big TR. So this is rarely used. If you're trying to get like a fast, quick evaluation of something, and there's sort of a need for speed, but not spatial resolution. If it's more geographical versus, you want that image to look nice and sharp. So there might be a few examples where you could use this, but it's just signal's going to go way down. So while fast spin echo has replaced conventional spin echo, we're not doing single shot fast spin echo very often. I click and nothing happens. Yeah. Disadvantage is the signal to noise. Okay. Drive, we are not going to talk about because this is, I think, too old and not being used anymore. But let me quickly see something. Let me go to Claude for a second. I'm telling you, I don't Google stuff anymore. Google's like lame now. Although I don't know, Gemini is okay. There's just so many other things to play with. So drive, which stands for driven equilibrium sequence, is still being used, though its popularity has evolved over time. I don't know what they mean by that, but mostly for neuro, CSF. Yeah, mostly neuro. Okay. The one thing I didn't mention to you, or did I? Is all of the acronyms that get used in. So I want to show you guys something. Have you guys started clinical yet, any of you?
Yep.
Or anyone actually just doing MR? Dennis.
I've been doing clinicals for the past 2 weeks now.
Oh, good.
I actually
So-
just came from clinicals.
Oh, so you have a long day today. Okay. So what you're going to want is something similar to, hold on, now you guys are in the way now. Sequence acronyms. Okay, so let me explain this. So this is not the only list. Actually, Claude gave me a much bigger list a few weeks ago. The registry is going to have the generic terms on the left, like spin echo, like fast spin echo, inversion recovery that we're going to talk about in a minute, which consists of stirs and flares, etc. But what you'll notice is here you have 5 different manufacturers, and they, once upon a time when things were old, everyone called spin echo spin echo. But then as MRI developed and these companies wanted to have a better edge and selling point, so besides faster gradients or stronger magnets, they came up with their own versions of certain sequences, and they had to give them proprietary names, right? So a spoiled gradient sequence, Siemens calls a flash, right? But Hitachi calls it RSSG. Where am I going with all of this? When you're doing clinic, and especially if you do clinic in multiple places with different manufacturers, like one place is GE and another place is Siemens, or you work in one place that has 2 different machines, you're going to want to be able to map the sequence that you see on the screen that might say something like lava, right? And realize that it's not really lava you're doing, right? Lava is actually a very fast gradient echo scan that a different company calls Vibe and a different company calls Thrive. You will not see any of these manufacturer terms on the registry because they are not sponsored by GE, right? So when you're doing clinic for your own learning purposes, you need to know, that Fiesta is actually a balanced gradient echo sequence, right? And that later on in the day, if you do a turbo FISP, well, that's what Siemens calls it versus GE calls it a Fiesta. For GE, it's a party, I guess. So you're going to want to, have something like this. You can put it in, you can ask a question to ChatGPT or Perplexity or any of the bazillions there seem to be now. If you're a big fan of Elon, you could use Grok. He has his own AI thing. Or you could use the new Chinese one that everyone's talking about. They almost look the same, honestly. And you can create like did I get rid of it? What happened to it? I think yeah, I was using it for school stuff too, updated calculations and whatever. Do I have it here? If it's in any of my old ones. I probably have it somewhere, but you just start a new chat somewhere and like give me MRI sequences. Acro. You can spell everything wrong. It'll figure it out too. By Let's see what it does. And then you could always, because you could always just fix it if it doesn't like what it gives you. Oh, so I don't like it already. I like them side by side, right? It's giving it to me like, yeah. So basically everyone calls a flare. So this is going to give you like the latest information based on whatever LLM they're using. But you have to be careful. You got to kind of have to double check things to make sure it's working. So they gave a Siemens, GE, Philips, Canon, Toshiba, and Hitachi. But here's something, because this is kind of old. Everyone calls a flare, except Hitachi. Don't ask me why they call the flare a flute. Everyone calls a diffused and weighted image a DWI. But you'll see again with the balanced and some of the newer sequences, they all have their own proprietary terms. So this is something you want to keep with you at clinic, so that when you're learning sequences, you know what the actual sequence type or generic term is. I kind of think about it as kind of like ibuprofen. Ibuprofen goes by Motrin, Advil, name a couple others. They're still they're essentially the same thing. All right. Any questions so far? Because we're going to get into brand new topic. I say we just power on. All right. Yeah, they're just doing interviews now, so I guess they're all out. Okay. So we've mentioned a few times that fat shows up bright. Fat shows up bright on a T2 and almost as bright on a T1. So it's just bad. Why is it bad? What do I mean? Well, we have different signal intensities, right? And those turn into different grayscales. But essentially, a high signal intensity, a bright area, if there's something kind of under it or nearby that is less intense, it's going to get swallowed up by the brightness of one tissue, making it harder to see the pathology or the other tissue. I use kind of an example where you're standing in front of your garage door and you take out a little flashlight. So you're facing it at the door, you see your little circle, but then a big 18-wheeler comes behind you with its giant lights facing just where you had your flashlight light. And basically what happens to yours, it gets swallowed up. You can't see it anymore. It just disappears essentially. If you could turn that light off, well, then you'd be able to see your little light again. And that's what inversion recovery does for us. It allows us to turn the signal off of anything we want. So we use it for fat suppression a lot to turn off that bright signal from fat, but we could use it for the silicone in a silicone implant and breast imaging. We use it for fluids all the time, so we can see lesions inside the spinal cord without the bright signal of the CSF getting in the way. Same thing within the ventricles. It's all part of what we call inversion recovery. It is a way to, the technical term is null the signal, N-U-L-L. It's a way to get rid of the signal. And it's cool. It's really cool. You can even null more than one tissue at the same time. So you could, let's say, null the signal from fat and null the signal from blood in a cardiac image, right? Within, the ventricles or the atria. So the way it works is, first of all, you have a kind of pre-sequence. So before the sequence even starts, so here's your sequence, here's your spin echo or fast spin echo sequence. Remember, it's 90, 180, 90, or 90, 180, 180, 180, and eventually a 90. But your sequence is taking place in this dashed area. The inversion recovery happens before, and we only have to do it once. And I'll explain that a little bit later. So what we have is a TI, which is time to inversion or inversion time. See, it follows the same way you say like TE and TR, right? But it's TI. Now, what you do is you have a 180, but don't get confused. It looks like this one, but this is the rephasing pulse. This is the inversion pulse. And what it does is it takes your net magnetic vectors. If you remember those vector diagrams, it takes all those net magnetic vectors that are precessing in the Z, and instead of pushing them down just to 90, it goes completely the opposite direction to 180. So it goes past 90 and then straight down. That's your 180-degree inversion pulse. But that's really not the most important thing. The important thing is, how long do we wait before the excitation pulse? That is actually our TI time. So the TI is the time between the inversion pulse, the 180-degree inversion pulse, and your excitation pulse. So let's fill in the blank. How do we get rid of one tissue type versus any other tissue type? Ding, 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 we vary the TI time. Sometimes shorter, sometimes longer, depending what we want to null, depending what tissue type signal we want to turn black or get rid of. So now the question becomes, well, is it on for a long time for fat, or not as much time for fluid, or, So here is the rule. You must write this down. If I said that the magic number for relaxation, remember, was 63%, my magic number for this stuff is 0.69. So here's the rule. If you know the T1 time, of the tissue that you want to null, and we do, because we know the T1 times of everything. It's like the science has been done already. So if you know the T1 time of the tissue you want to null, you multiply it by 0.69. And that number in milliseconds is your TI time. So if fat is about 300 milliseconds for T1, multiply that by 0.69, which is 207. Our TI time would be 207 milliseconds. You got that, Nestor? Okay.
Yes.
Now, picture where it's had some nice weather today, and tomorrow's supposed to be pretty warm. I don't know if I want to go to the pool just yet, but we're getting there. So picture a pool, and the surface of the pool is called the null point. Anything that's at the bottom of the pool that is floating up, that makes it to the surface of the pool, yields a signal. Anything that does not yield a signal. Now, let's say we have, I don't know, ping pong ball, golf ball, basketball. They're chained to the bottom. We cut those chains, they start floating up. Any one of those that doesn't make it to the surface, to the top, does not yield a signal. Now, if we exchange those for tissues, any tissue that doesn't make it to the top doesn't yield a signal. Now, why do we only have to do this once, but this thing keeps repeating and repeating? Is that once I push them down, because of this TI time, one of those tissues will not recover up to the null point. And then, before it gets a chance to recover, it's hit by other pulses. And then it keeps getting hit by other pulses. So it will just never recover. It's kind of like good luck trying to walk up an escalator going reverse. Right? You know, unless you speed up, if you go at the same speed, you're just going to stay in one spot and you're just never going to make it up. So that's why you actually only have to do this once, right? So it's inversion 180, followed by 90, followed by 180, then back to 90. So it's going to be like 180, 90, 180, 90, 180, 90, 180. This never has to happen again because they keep smacking those tissues down so that they never recover and they never reach the null point, and thus they never yield a signal. It's pretty cool when you think about it. Did I confuse everyone, or is everyone like sort of okay? Right. So the key thing here is, in order to set your TI time, which is already programmed into the machine. I mean, why should you have to look up the T1 time of a particular tissue, right? But it automatically knows how long to wait between that initial inversion pulse, this 180 inversion pulse, and the actual excitation pulse. So we commonly use two big ones. One is a flare, which this one happens to be. So flare stands for fluid attenuated inversion recovery sequence, FLAIR. That's the IR. The other one is STIR, which is for fat suppression, and it's a short tau inversion recovery. Again, at the end of the word, IR. So they're both inversion recovery sequences. Just one is for fluid, and when we say fluid, we mean blood or CSF, essentially. And when we say fat, we mean fat. And the number is not always exactly the same. You'll see a couple slides and you're going to be like, you know, there's a slight range because sometimes you have like kind of like really dense fat, and, you know, fat goes by different names, like adipose tissue is basically fat. There's a lot of different ways to say fat within the body. And that's kind of how you do it. So what's nice about, you know, a flare is if there was some like tiny little lesion or something like right around the edge. Could you imagine if this was just as bright as everything else over here? You wouldn't be able to see it. You could easily miss it. So what do these inversion recovery techniques do is they create contrast, essentially. They give you better contrast for what you're, looking for. So that's what this is saying, being able to essentially turn off the bright signal so that you can see less bright signals that would have gotten swallowed up or would have been, just easy to miss, just increases the overall contrast in your exam. So it's another level that MRI can do, besides weighting in general, that CAT scan can't do, or X-ray. Like, not even close. So without sounding like a little hypocritical, in CAT scan, and of course, just about everything you can do in CAT scan, you can do in MRI. So in CAT scan, you can also do what's known as a MIP, or maximum intensity projection, which is turning individual pixels on or off. So for instance, you want to do a CTA, a CT angiogram, and a vessel kind of zigzags on top of a bone. So the bone appearing bright would get in the way of the vessel also appearing bright. So if you could turn the bone off and make it black, then you see your vessel. And that's exactly what you can do, because the computer, even though the pixel for the bone and the pixel for the blood in the vessel, or the contrast in the vessel, looks almost the same, they both look just as bright. There's a subtle difference numerically that the computer knows that you can't actually see. And you basically tell the computer, if you, in quotes, see bone, turn the pixel off and make it black. So there's no reason you can't do that in MRI also, right? Analyze the pixel brightness levels, right? So that's the only reason I diverge into CAT scan a little bit, is because you could do that in MRI also, but you cannot do fat and fluid suppression in CT. It just doesn't work that way. So here's another nice, timely for a couple of years ago. There was that whole monkeypox thing in New York City. But this is a nice flare. So whenever you see the ventricles or like kind of the edge between the skull and the soft tissue nice and dark, then you know it's a flare. The only time that you change things up is when you use gadolinium, which we'll talk about. You cannot do a STIR, S-T-I-R. Because remember, we talked about how do we figure out our TI time? It's based on the T1 time. But we will see, so preview to that lecture in the future, that when you inject someone with gadolinium, it's the only thing that will alter the actual T1 time of a tissue. Right? So if you're going to use gadolinium, you cannot do STIR. You have to do a different inversion recovery technique that varies by one letter. It's SPIR, S-P-I-R, instead of S-T-I-R. But don't worry, we're going to talk about it because we didn't even get to that. So the parameters in inversion recovery are, keyword here, mostly the same, except for T1 weighting. So don't ask me why. T1 weighting for inversion recovery. So the actual difference between medium TI, long TI, that's not that important. But because again, you're going to be basing the actual inversion time on the tissue that you're trying to null based on 0.69. But it's this part. So short TE, this is not a typo. This normally would be short TR. That's what you want for T1 weighting. But I'm pointing it out here that it's long TR. But everything else is okay, right? For proton density weighting, it's a long TR and a short TE. That combination kind of messes up T1 and T2. Pathology weighting, which is essentially the same thing as T2 weighting. So if you see the term T2 or you see pathology weighting, it's the same thing. So a long TE and a long TR. Okay. So stir versus flare, notice the IR in both of those. When we get to gadolinium, we'll talk about the other one, which is SPIR. It's a different, not as good, different way of suppressing fat. Oh, yes. And of course, we can do inversion recovery, whether it's a routine, regular spin echo sequence or a fast spin echo sequence. So this is what I was kind of describing earlier, right? So stir, short tau inversion recovery for fat suppression. You hit it with the 180, everything goes down here. The null point is at 90 degrees. That's what I described as the surface of the pool, right? So as long as you don't get to 90, you will be essentially nulled, right? And that U is the tissue, right? So whatever the tissue is that doesn't make it to the null point will not yield a signal. So here's a nice stir, right? If this was a regular X-ray, you'd be like, what's going on here? It looks like you reversed the image, right? But this is not that. This is all that fatty, bony marrow inside that turns dark, right? Because it is not allowed to express a signal. So we're using approximately 100 to 175 milliseconds, which fits in closely with our 0.69 for times the T1 time of fat. But it can allow us to see lesions and get better views kind of in the joint spaces in here. Right. So this is a nice example of a stir. Right. The monkeypox thing we saw earlier was a good example of a flare. Right. So the TI required to null signal from a tissue, as I've mentioned, but now it's in writing, so you can't say you never saw it, is 0.69 times the T1 relaxation time. So there are some kind of general parameters that you can kind of look at, but this is the stuff that you want to write down and start bringing to clinic and seeing if it actually makes any sense, right? Because what's the major things you can see on the scanner? Your TR, your TE, your TI, those times are there, right? And you can change them, but they're there. So when you're in the clinical environment, you know, make note of what the TR, the TI, the TE, or any of the other times are when you are scanning, right? Take that extra second. Take a picture. Just don't get any important information. No accession numbers, no names, no medical record numbers. So flare basically like a stir, but for fluid. Right. It's going to be a bigger difference because the T1 times are different for fat than they are for CSF. But it's still the 0.69. Right. So like I think you might have missed this, Jewel. Here it is in writing, 0.69 times the TI. Excuse me, times the T1 to give you the TI. Okay. So here's another flare. Most of the scan times have gone down in general, so it's not going to take 20 minutes anymore. So this slide is related, we're almost done. This slide is related to the fact that I said, look, how cool, you can actually know the signal from more than one thing at the same time. So you can have 2 or even 3 TIs, right? So if we go back for a second, yeah, there's no reason I can't have inversion with another inversion with another inversion and then have a 90, right? That would be a double or a triple prep, it's called. So your sequence would start at the same time, but different tissues would be not getting to the surface of that pool in my sort of story. Okay, so there's a double IR prep, right? So like I said, it uses 2 180s. And it's going to null blood. And there's a triple one, right, that can null fat and blood. So, I mean, anything can become, can be delved into in more detail. I'm going to see if I can't get a little bit more information on double prep versus triple prep. I see I already have a note to myself that I didn't see. Let me read my own. Double 180 IR prep is good, I guess, for heart and great vessel imaging. Triple is, so this is getting very specific, right? Triple is good for looking at the fatty infiltration in the heart walls. Yeah, so I mean, there's so many different types of MR procedures and scans that you can't possibly know everything, right? You will discover that when we start to touch a little bit, we don't even barely scratch the surface of cardiac imaging, but we do talk about gating. And you really need to know what you're doing when you're doing gating. It's not just setting up the leads. You know, that's the easy part. It's like running the software and all that stuff. And then at the end of the course, which is kind of the sort of one of the more fun lectures to me, because it's kind of like newer versus older stuff when it comes to sequences like perfusion sequences, spectroscopy, the big one that is on all the TV shows like fMRI, functional MRI. Fascinating and very, very interesting, but the registry might ask a tiny question, but there could be a course on any of those, or at least a much bigger lecture than the 40 minutes that I give to it. All right, everyone. So I will send you the PDF. I think it's called an interactive taxonomy of pulse sequences. However, it's no longer interactive, as I mentioned. That's really good. There's other resources out there, questions and answers in MRI, but the most I think you'll get out of pulse sequences is clinical, right? bring your little notebooks and your acronym sheet so you know which sequence you're actually studying for, versus whatever the manufacturer calls it. And, you know, write down your TRs and TEs and what you see and what you don't see and what, here's a very important one. The spin echoes are good for like all weighting T1 and or weighting T2. The other ones lean towards a particular weighting, right? They're not as, I can do everything with them, right? Which reminds me, I also have an Excel spreadsheet that I will send you that has, this one I didn't chat GPT it. I had to make it myself once upon a time. It has different sequences, what they're used for, what the particular weighting is. So it's got some information kind of all in one nice place to see. All right. Any questions, thoughts, observations? And I'll send you that little worksheet or kind of 10 question test next week for you to give me the following week. We're good?
Yep.
All right, everyone. So stay safe, enjoy the weather, and I'll see you next week.
Okay, see you next week.
Have a good
Good night.
weekend.
Bye, guys.
Bye, Professor.